resistor, resistor, and the inductor out here. We're looking for the current. And so before t equals 0, things have stabilized. The inductor acts like a short circuit. So what we think we've got here is 50 volts, 2 ohms, and a short circuit. We're interested in the current through the short circuit, and so that's Ohm's law would tell us that I is equal to 25 amps. So I0 equals 25 amps. Okay, then what happens? Then after T0, the voltage source kicks up. Now we've got 100 volts. The 2 resistors. And we're still looking at this current. And now things, when we look for I infinity, we say, okay, things have changed at 0, but now they've had a chance to stabilize. And now that they're stabilized, what's going on? Well, now that we're stabilized, we've got 100 volts, 2 ohms, and the inductor, which again looks like a short circuit. So that's 50 amps, isn't it? Okay, then the other thing is, what is tau? Well, we're interested in tau after the thing has switched, but before we've gotten out to time infinity. So we're looking at this circuit here, 2, 6, and we know what L is. L is 3, and tau is going to be L over R, so 3 over whatever R is. Well, what is R? Well, we look at this thing, and one thing we could do is say, what's the Thevenin equivalent? And for the Thevenin equivalent, we'd basically look from the inductor terminals back, and what do we see? We see 6 ohms and 2 ohms in series with a voltage source, but for Thevenin, a voltage source is a short circuit. So we've got 6 ohms in parallel with 2 ohms. Okay, so that's our resistance that we need for L over R. And 6 in parallel with 2, it's 2 in parallel with 6. 2 times 6 over 2 plus 6, that's like 1.5. So L over R is equal to 3 over 1.5, which is 2. And so now we can say that I of t is equal to I infinity, that's 50, plus I0 minus I infinity, so that's 25 minus 50, so minus 25 e to the minus t over 2 amps. Okay? Okay, here's one, and would like to find the capacitor voltage. So let me bring these two out as V of t. Okay, so we've got a 7.5 U of t milliamp current source, 20K resistor, 30K resistor over here, and the capacitor. And again, basically, I think the easy way to deal with this is to convert the current source and this parallel resistor into a Thevenin equivalent voltage source and series resistor. So when we do that, what do we get? Well, the voltage is going to be the current times this resistance. So that's 7.5 milliamps times 20K. So that's 150 volts. I should say 150 U of t volts. And then the 20K goes in series, 20. And there's a 30K over here, which will be in series with that. So put that here, 30. And then the capacitor. And now this is pretty straightforward thing to analyze, because I should put here V of t. What is V0? V0 is the source is still off, so no volts coming in anywhere. So V0 is equal to 0. V infinity is equal to what? Well, we've got 150 volts, total of 50K of resistance, and the capacitor. Well, the capacitor looks like an open circuit at infinity, so there's no current flow through the resistors. So that means V infinity is 150 volts. Now what about tau? Tau is equal to RC, and that's this 50K times 0.1 microfarad, and that's equal to 1 over 200. So now we can say that V of t is equal to V infinity, that's 150, plus V0 minus V infinity times the exponential. So times 1 minus e to the minus 200t volts. Okay? Okay, let's say we've got this circuit. We've got a capacitor and a couple of voltage sources, a 4-volt source and a 2-volt source. and a switch that opens at T0. We want to know what VT is. So since when the switch is closed, which is up until T0, we've got the 2-volt source directly across the capacitor. So that means that V0 is going to be 2 volts. Now this 4-volt source is out here, but there's a resistor, and so it's it's got 2 volts across this 60K resistor. It's just sitting out there not doing much. Then the switch opens, the 2-volt source goes away. Okay, now what's V infinity? That's 4 volts, isn't it? And tau is equal to RC, which is 60K times 2 times 10 to the minus 6, and that's 0.12. So now we can say that V of t is equal to V infinity, that's 4, plus V0 minus V infinity, so 2 minus 4, so minus 2 e to the minus t over tau, and so that'd be t over 0.12 volts. Okay?
Got a question about the notation.
Sure.
So with the arrow in the middle, arrows pointing upwards, I'm assuming that the upper portion of the capacitor is positively charged, the bottom portion is negatively charged.
Yeah.
That's kind of counterintuitive, given that voltage source is positive and negative.
Well, no, there's what we're saying is, like with this part, we've got a plus volt here, and that's connected to this terminal.
Well, no, my point is that voltage source is positive and negative, so you think that the arrow is pointing down?
No.
I've just never seen that notation, so I want to understand the intuition behind it.
Well, it's just that if we look at this thing, and if there's current running into this top terminal, that's going to be plus. Now, it's just like if we had a resistor out here, and we had current going into that resistor, what would the voltage be? It would be plus and minus, right? And same sort of thing here. In this case, once we've opened the switch, there's 2 volts at this terminal. There's 4 volts right here. So there's current flowing through that resistor, and that current is going into this top terminal of the capacitor. And so we've got current coming in, and that'll make a voltage that's positive at the top and not at the bottom. Does that make sense now? Not really.
I'll figure it out later.
I mean, we could invert it if you wanted, and then we would say that V of t is minus 4 plus 2 e to the minus t over 0.12. We would just end up inverting what we've calculated. Yeah, take a look at it. That's something that was defined early in the book, and basically it says that we can take most anything, have 2 terminals, and what we'll do is we'll say that if there's current going into this terminal and the voltage is plus and minus, then this thing is absorbing energy. And if the current's going the other direction, it's providing energy. And when this switch opens, even though this capacitor has 2 volts on it, it's going to absorb more energy because it's going to be getting charged up to 4 volts. Take a look at it.
Rewrite it in just one voltage source and step up?
Yeah,
And would that help us in any application?
maybe, I don't know. Converting it over to a unit step, I don't know, the thing that would change with that is we want the resistor to be in when it's being charged from 2 volts up to 4 volts. I guess we could say uh, 2 plus 2 U of t volts, 60K capacitor. Okay, how would this behave? Well, at T0, what do we have? This is 2 volts. And this thing has been charged up so that it has been charged up over time so that V0 is 2 volts. Then after T0, this thing is going to become 4 volts, and we would get the same equation. But what it doesn't show is that in this case, we can see that here we've got a source that's directly in parallel with the capacitor. So it didn't have to be with the switch closed for any long period of time to build up the charge on the capacitor. It happened instantaneously. Whereas here, when it's 2 volts, it has to have been at 2 volts for a long time so that the capacitor will be fully charged. So it's not an exact equivalent, but it's certainly good enough for getting the behavior of the circuit. Yeah, that's a good question. I'm going to show you this, and then I'll be drawing it, but I want you to see what it looks like just to get a feel for it at the beginning. Got 120 volts, 10 ohms, a switch over here, there's another resistor, 50 ohms, and a capacitor. We want to see the voltage across the capacitor. Then the switch flips, and the 120 volt source goes away. But now we've got 50 volts, 60 ohms, 200 ohms, and this resistor is still in here, and the capacitor. And we'd like to find the voltage across the capacitor. Okay, so what's it look like before t equals 0? Before t equals 0, we've got 10 ohms, 120 volts. It comes over, there's a resistor that comes down, 50 ohms, capacitor, And this is 0.05 farads. And we're looking for V of t. Okay, so this is pretty straightforward. What we've got here is something, there's a voltage divider here, isn't there? Now, before t equals 0, we think things have all stabilized nicely. And so the capacitor is an open circuit. And so we've got 120 volts, 10 ohms, 50 ohms, and we need to know the voltage across the 50 ohm resistor. So V50 is equal to 120 times 50 over 50 plus 10, which is 100 volts. And that's V0 for the capacitor. Okay, so that's one of the three things we need to know. Now, how about after T0? Well, now the circuit changes a bunch. We've got 50 volt source, 60 ohms, 200, 50, the capacitor. Okay, so what have we got here? Well, to begin with, the 200 and the 50 are in parallel. So we could replace those with something that's 200 times 50 over 200 plus 50. So that would be 40 ohms. So we've simplified it already. So now we've got 50 volts, 60 ohms, 40 ohms, and the capacitor. Okay, and now another voltage divider, 50 volts, 60 ohms, and 40 ohms. That's 50 times 40 divided by 40 plus 60. So that's 20 volts. So we have a 20 volts. And what is the impedance? Well, the impedance is what we need to do is we need to calculate tau, is 0.05. And so we take a look at this equivalent resistance, which is 60 in parallel with 40. That's 24 ohms. That's 0.05 farads. So 24 times 0.05, tau is equal to 1.2. And we know from this we have 50 volts. So V infinity is equal to 20 volts. So now we've got all that we need, right? We can say that V of t is equal to V infinity, that's 20, plus V0, which was 100, minus V infinity, 100 minus 20, that's 80, e to the minus t over 1.2 volts.
Professor, shouldn't 60 and 40 be in series because the capacitor is an open circuit?
I don't quite understand your question here, but you're probably asking for what's the resistance?
Yeah.
Okay, and so the resistance is what we would see, and it's like taking a Thevenin equivalent of what's connected to the capacitor. And so what do we got? We've got a voltage source, 60 and 40 ohms. And so the Thevenin resistance of that is replace the voltage source with a short circuit, and now we've got 60 in parallel with 40.
Okay, fine.
And 60 in parallel with 40 is 24.
Yeah, fine. Thank you.
Okay, does that make sense now?
Yes, it does. Thank you.
Yeah, basically, what we have to do is when we're calculating tau, we need to go and take a look at what's connected to either the capacitor or the inductor and find the Thevenin equivalent resistance. And we use that in our calculation for tau. Okay, we've got this circuit, 24-volt source and a 2-ohm series resistor connecting up to terminal B of the switch. Terminal A of the switch goes to an 8-amp current source pointing downward that's in parallel with a 10-ohm resistor. And we've got a 0.2 of a Henry inductor there, and we're looking for the current down into the inductor, so I of t. And so let's look at it first. The switch starts out in the position where it's shown, position A. It's been like that for a long time. So we've got 8 amps coming around, going into the bottom of the inductor. The inductor will look like a short circuit because this has stabilized over time. So I of t, which is pointed the other direction, we would say that I0 is equal to minus 8 amps. Then switch flips, and now we'll look at what's going on at infinity. And there we've got a 24-volt source. I should show a plus and minus, plus at the top. 2-ohm resistor into the inductor. So the inductor will look like a short circuit out at T infinity. And so we've got 24 volts, 2 ohms. So I infinity is going to be 12, let's write this right, 12 amps. Now what about tau? Well, we can ignore all this stuff that's on the right because the switch flips. For tau, we're looking for L over R, which is 0.2 over 2, which is 0.1. Okay, so right now we can write down I of t. I of t is equal to I infinity, that's 12. That's 12. Plus I0 minus I infinity. Well, I0 is minus 8. Minus I infinity would be another minus 12. So that's going to be minus 20 e to the minus t over 0.1 amps. Okay, we've got a 90 volt source over on the far left, 400K in series with it, connected to a half microfarad capacitor. And the other side, when you flip the switch the other way, we've got a 40 volt source where plus is going down, not like we would normally assume up, and 20 ohms and 60 ohms. And the switch flips to B at T0. Okay, so before the switch is flipped, what have we got? We've got this 40 volt source, total of 60 and 20 ohms. And so that's a voltage divider. So we're going to have, out of this 40 volts, 30 volts will be across the 60 ohm resistor and 10 across the 20 ohm. But that's going to be a minus 30 volts that we'll see. So we can say that V0 at the capacitor is equal to minus 30. Then we switch the flip. Oh, I said that wrong, didn't I? We flipped the switch. And now we've got 90 volts series resistor into the capacitor. So V infinity is going to be equal to 90 volts. Tau is going to be RC, and that applies after the switch is flipped. So tau is equal to RC, which is 400 times 10 to the third times 5 times 10 to the minus 7, and that's equal to 0.2. Is that right? Yes. Yeah, that's right. 4 times that would be, yes, that's 0.2. Okay, so now we've got what we need. We can say that V of t is equal to V infinity, that's 90, plus V0 minus V infinity. So that's plus minus 30 minus 90, so minus 120 e to the minus 5t volts. So what it means is we could look at the waveform. It starts out at minus 30, goes up and settles into 90. Okay? this wrong. 20 U of minus T amps. 20 U of minus T. What does that mean? That means that it's 20 up until T equals 0, and then it drops to 0. So it's sort of a backwards unit ramp. Okay, so it's just a T0. We want to know, and we're looking for current through the inductor, I of T. And so at T0, we've got 20 amps going in, and there's a resistor, the inductor, another resistor. They're all in parallel, but the inductor will look like a short circuit. So all of that current's going to go through there. So I0 is equal to 20 amps. Now for I infinity, at T0, the source goes away. So that means I infinity equal to 0. Now what's L over R? L over R. And so now L is equal to 2, and R is equal to 10 in parallel with 1. So what is that? That's 10 over 11, so let's say 0.9. And so that would be equal to 2.2. Okay, so now we can write things down. I of T is equal to I infinity, that's 0, plus I0, which was 20, e to the minus T over 2.2 amps. Okay, we've got 24 volts, 3K resistor, and a 5K resistor. There's a capacitor in the, oh, this is 0.5 millifarads. And the switch, and then the other side is, once the switch has flipped, we've got a 4K and a 30 volt source. Okay, so we can look at it, and we need to find V0. For V0, well, the circuit we've got is this. We've got 24 volts and a voltage divider that connects to the capacitor. So 24 volts, the voltage divider is going to be, what, 15 volts? Yeah, we've got, because 24, we'll have 9 and 15, yes. So V0 is equal to 15 volts. V infinity, now the switch is flipped and we get the full 30 volts. Tau is equal to RC, which is 0.5 millifarads times 4K, and that's equal to 2. So V of t is equal to V infinity, that's 30, plus 15 minus 30, so minus 15 e to the minus t over 2 volts. Okay, does that make sense? Well, I think this is a good breaking point for today. Are you all comfortable with that? Okay, good. Well, in that case, let me wish you all a good, comfortable, safe, happy weekend.
Thank you.
Thank you. And I told you all that I got my second COVID shot on Monday. And when I took my first COVID shot, there was no effect whatsoever. But for my second one, middle of the night on Monday, I'm in bed. I've got an electric blanket going at high heat, and I'm just freezing, just trembling. I'm so cold. So I had to put an extra bathrobe on and get back underneath the hot blanket. And after a few minutes, it passed. And I felt tired yesterday because I didn't get very much sleep Monday night. Because after this happened, I kept trying to go back to sleep and kept thinking, well, if I go back to sleep, it's going to happen again and such. Anyway, today woke up feeling like $1 million. Had a good sleep last night. And so when you get a chance, get the vaccine.
My arm was incredibly sore after the first dose.
Yeah. Yeah, for me on the first one, I wasn't sore at all. Just a little bit of tenderness where the shot went in, and that was it.